Welcome to the video lecture on conic sections. Conic sections are the curves formed by the intersection of a plane with the two napes of a cone. This picture that I'm going to show you comes from your textbook, and it shows you the way that these conic sections are formed. In the first case, we have a plane cutting through a cone parallel to the base, and the shape that's formed here would be a circle. If you draw that plane intersecting sort of at an angle, then the shape that we get formed is called an ellipse. If we draw that plane sort of going at an angle towards the base, then we get this parabola shape. And then if we have our plane intersecting both cones simultaneously, then that creates our hyperbola. In this lecture, we're going to be talking about these last three cases. So the parabola, the ellipse, and the hyperbola. So let's start with parabolas. We've already studied parabolas from an algebraic point of view. We know that the equation f of x equals ax squared plus bx plus c has a set of solutions that lie on a U-shape. We can determine, depending on the values of a, b, and c, whether the parabola opens up or down, where the vertex is, where the intercepts are, as well as finding additional points on the graph. If we know that our function is ax squared plus bx plus c, and that leading coefficient a in front of our x squared is positive, then you should already know that that gives us a parabola that points up. And the vertex of this parabola corresponds to the minimum value. If this leading coefficient a is negative, then we know we have a parabola that points down, and this time the vertex corresponds to a maximum. The vertex of a parabola is very important, and we have a formula for figuring out what it is. If we want to find the vertex, we just let x be minus b over 2a, where we're using the b from up here and the a from up here, and that's your x coordinate, and then you would take that value, substitute it back in for these two x's, substitute that in and figure out what it is, and that'll give you your y coordinate of your vertex. So what we're going to do now is define conic sections from a geometric point of view instead of an algebraic point of view, and we're going to show that these two different definitions are consistent. So let's talk about the geometric definition of a parabola. A parabola is considered to be the set of all points equidistant from a given point called the focus and a given line called the directrix. So here's my parabola, and there's this point called the focus inside of our parabola. And there's a line outside of our parabola, and in fact it's below it, called the directrix. And what this parabola represents is all of these points P, where the distance from the point P to the focus, so this distance right here, is equal to the distance from that point P down to the directrix. So these two line segments have to have the same length. If we look at a different point, that same relationship has to exist. So the distance from point P sub 2 to the focus, which would be right here, has to be the same as the distance from point P sub 2 down to the directrix. So these have to be equal, and these have to be equal. And all of the points that satisfy that relationship create your parabola. So what we're going to try to do next is come up with a formula for what the equation of a parabola would have to be based on this definition, this geometric definition. So we're going to start with a parabola centered at the origin, and that's mainly just to make our life easy. We're going to pick a point P to be some random x comma y, and our focus is going to be some point inside of a parabola, and I'm going to call its coordinates 0 comma p. It lies on that y-axis, so its x coordinate is 0, and I'm going to let this distance from the origin up to that focus be p. Now, since by definition of our parabola, the distance from the origin to our focus has to be the same distance from the origin down to our directrix, this downward distance here must also be p, which means that the equation of this line for the directrix would have to be y equals, because it's a horizontal line, negative p. And it has to be a negative p because we're below the x-axis and we're going down a distance of p. So what we're going to do next here is come up with our geometric restriction, and that was based on our definition of this parabola. We said that the distance between our point P and our focus, so this distance right here, so the distance from point P to the focus has to equal the distance from the point P down to the directrix, which is this distance right here. So we want these two distances to be equal. So let's figure out what each of these are, and then we're going to set them equal to each other and solve. Now, to get the distance between point P and point F, this focus, we're just going to use our distance formula, which comes from that Pythagorean theorem, and it's the square root of the difference in the x's minus, or squared, the difference in the x's squared plus the difference in the y's squared. So we're going to take this x minus this x. So x minus 0, and we're going to square that, and then we're going to add to that the difference in the y's. So this y minus this y. So y minus p, quantity squared. And if we simplify that, x minus 0 is just going to become an x squared. So here's what we have for this distance between point P and the focus. Now let's find the distance between point P and our directrix. Now to get that, this is just a vertical distance going up and down because they share the same x coordinate, these 2 points. So to find this vertical distance, it's just whatever this height is, which happens to be y, minus whatever this height is, which happens to be this minus p. And I'm going to use absolute values just to be safe so that we're making sure we're getting a positive distance. So again, it's just the height of our point P, which is what we called y, minus the height of our line, and its height was minus p. Minus minus becomes plus, so this is just y plus p. Now, based on our definition, these two distances must be equal. So I'm going to set these two things equal to each other. So here's between the point and the focus, and that has to equal between the point and the directrix. Now, to try and simplify this to come up with a cleaner looking equation, first thing I'm going to do is get rid of my square root by squaring both sides. So if I square away that square root, we're just left with x squared plus y minus p quantity squared. And when you square away that absolute value, we can lose it because this y plus p quantity squared is going to be positive anyway because we're squaring it. So we don't really need those absolute values in there anymore. Now let's go ahead and FOIL these things out to see if we can simplify things and cancel out like terms. So we're going to get an x squared. If I FOIL this out on the left, we're going to get a y squared. We're going to get a minus 2py in the middle plus a p squared on the end. And over here we're going to get a y squared plus a 2py plus a p squared. Now if I go to subtract my y squareds, they're going to cancel each other out. And if I go to subtract my p squareds, those are going to cancel out as well. However, my 2py's will not cancel out because they have opposite signs. So if I add this 2py over to the right side to try to get this x squared by itself, we'll end up with a 4py on the right hand side. And this is the equation of our parabola. Sometimes we prefer to solve this for y, and that would require dividing through by that 4p. Either equation is fine. So what we just came up with is if we force these two distances to be equal, it forces us to be on a curve that has to have this type of an equation, which is exactly what a parabola looks like when we talk about our algebraic viewpoint, because it has an x squared and it has a y to the first. So let's summarize our results here. Now, if you have a parabola with a vertical axis, this is what it's going to look like, and this is what we just proved up above. Its equation will look like x squared equals 4py, or if you solve that for y, you get 1 over 4p times x squared. The vertex of this parabola is at the origin. Its focus is along the y-axis inside of our parabola at coordinates 0 for x and p for y. So this p in our formula is important because that's going to tell us where our focus is. The directrix is outside of our parabola, below it or above it, depending on which way it points, and its equation will have y equals negative p. So this is kind of what the graph would look like if we have a positive p. So if p is positive, then we're going to have a parabola that points up. The focus will be on the inside at 0, p, and the directrix will be down below at a height of minus p. If p is negative, then we're going to have a parabola that points down. Still the focus is on the inside at that 0, p, and the directrix will be outside of the parabola at y equals negative p. Now something we call the focal diameter. The focal diameter is the horizontal distance across, just like this. So that is this 4p right here. And sometimes if you want, you can even have absolute values around those depending on whether p is positive or negative. So that's just a definition that you sometimes see reference to. Focal diameter is just this 4p that we see in our formula. Now what if we have a parabola that's not going up and down but has a horizontal axis, so side to side? Then its equation will look very similar, but this time it's the y that's being squared instead of the x. So we get y squared equals 4px, or x equals 1 over 4py squared. Still our vertex is going to always be centered at the origin, but this time our parabolas will be either opening to the right if p is positive, or to the left if p is negative. If p is positive, we're going to point to the right, and that focus will be on the inside at p, 0, and this time our directrix will be a vertical line with equation x equals minus p. If p is negative, our parabola points to the left, the focus is still on the inside of our parabola, and our directrix is still a vertical line with equation x equals minus p. Now you might be saying, well, why do we need to learn a whole new approach to parabolas? And the reason why is because this idea of the focus is very important. It has a lot of applications in science and engineering. And one very important application that I'm sure you use every day is the headlights in your car. Imagine your headlight. These are shaped like parabolas, and the light source of the headlight is located at the focus of this parabola, if you can imagine sort of a coordinate system right here. And what happens is the light source points towards the vertex, and as a result, because of the curving shape of that parabola, the light is then reflected back out, and that's how our headlights work. And telescopes work exactly the same way. So you do see applications of this focus and this parabola in science and engineering. So let's practice using our new formulas. So here we have y equals negative 2x squared, and we want to find the focus, we want to find the directrix and the focal diameter, and we want to sketch the graph. So notice that this has the x being squared and y to the first power. So this is like your normal parabola that's going to either point up or down. It's a vertical axis. So this is going to be a parabola that goes vertically, and because this leading coefficient in front of that x squared is negative, we know that this is going to be pointing downwards. So it's going to have a graph that looks something like this. The focus is going to be inside of the parabola down here somewhere, and the directrix would be outside of the parabola up here. So let's see if we can come up with some of these equations. So if we compare this to our general formula up here for our vertical parabolas, the formula is x squared is equal to 4py. So this is supposed to look like x squared is equal to 4py. Or if you were to solve this for y, that's that x squared over 4p. So if we have that y is equal to negative 2x squared, then this y has to equal 1 over 4p times x squared, but it's equal to negative 2x squared, so that forces this 1 over 4p to be this coefficient negative 2. So what we're going to do is we're going to set 1 over 4p equal to negative 2 so we can solve for p. The reason we need that p is because that's what tells us our focus, and that's what tells us our directrix, and it tells us our focal diameter. So how do we solve this for p? Well, we can just cross multiply. I'm going to multiply both sides by 4p, and this becomes negative 8p. And if I divide by negative 8, that tells me that p is negative 1/8. So my focus is down here at 0 for x, because we're on the y-axis, comma, negative 1/8. So now we know the focus. The directrix is this horizontal line, so it's going to have equation y equals positive 1/8. It's the same p, but going in the opposite direction. So now we know our directrix. And finally, that focal diameter is just that formula 4p. We mentioned that up above here. So here's our focal diameter, 4 times p, and in this problem our p was this negative 1/8, so this would become negative 1/2. Personally, I believe that focal diameter should be considered positive because a diameter, I think, of a distance. So I am going to say that my focal diameter here, I'm going to take an absolute value of this, is just this 1/2. Okay? Alright, let's try another example. 16x minus y squared equals to 0. So if we separate our 16x and our y squared and put them on opposite sides, I want you to notice that this time it's the y that's being squared, not the x that's being squared. So this time this is going to be a horizontal parabola, one pointing sideways. And if we wanted to solve for x, we would bring that 1/16 over next to that y squared term. You can do that if you want, you don't have to. And what it tells me is that that coefficient of that y squared is a positive number, so that means this is going to be a parabola that's pointing to the right. And its focus is going to be somewhere inside, and its directrix is going to be a vertical line on the outside. So we need to find out what p is in order to figure out where our focus is and where our directrix is. So since this is a vertical parabola, we're referring to this formula right here, solved for x. X is equal to 1 over 4p times y squared. So this is supposed to equal x equals 1 over 4p y squared. So that forces 1/16 to equal 1 over 4p. And if I cross multiply, we get 4p equals 16, divide by 4, and that tells me that my p is 4. So that means this focus must be at 4 on the x, because remember, this time we're going sideways, so this point right here would have to have an x coordinate of 4, and it's on the x-axis, so the y coordinate is 0. And the directrix would be this vertical line, and vertical lines are x equals, and if the focus is 4 to the right, then the directrix would be 4 to the left, which would make it x equals minus 4. And then finally, our focal diameter is just 4 times p, so 4 times 4 makes it 16. Okay, next equation, or next example. Find the equation of a parabola that satisfies the following conditions. We want the vertex at the origin, and we want the focus at 5, 0. So let's visualize what this would have to look like. If the focus is at 5, 0, that's along the x-axis. So the only way that can be on the inside of our parabola is if our parabola is pointing to the right. So we're talking about a sideways parabola with its vertex at the origin. So in order for this to work, we're going to be needing to use our parabola that looks like this with this kind of format to it. So we want the y to be squared, and we want that to equal 4px, or you can use this version of it. Both of these are equally available to use. It doesn't matter which one you use. So y squared is supposed to equal 4p times x. And what's p? Well, that's exactly what your focus is. That's why the focus is good to know. So if our p is 5, then 4 times 5 makes this 20x. So the equation of this parabola must be y squared equals 20x. In part B, we want our vertex to be at the origin, and we want the equation of our directrix to be y equals 6. So let's visualize this. If our directrix is at y equals positive 6 up here, remember the directrix is outside of your parabola. So if our vertex is at the origin, this has to be a parabola that's pointing down with the focus on the inside down here. So the focus would have to be at 0 for x, negative 6 for the y. And that's good to know because that tells you your p. Your p is exactly wherever your focus is, so that's going to be negative 6. So we want our p to be minus 6, and since this is a parabola that's pointing vertically down, then we want to be using the formula with the x being squared equals to 4py. And if I substitute in negative 6 for that p, then that means this equation would be negative 24y equals x squared. Okay, the next one here. Now we want our focal diameter to be 8. We want the vertex at the origin, and we want the focus on the negative y-axis. So if we want the focus on the negative y-axis, that means we want it down here somewhere. And they're not telling me the exact coordinates, but I know that the x-coordinate would have to be 0, and the y-coordinate would be whatever that p is. So do I know what p is? Well, I know the focal diameter. And remember, focal diameter is 4p. And if we want that focal diameter to be 8, then that forces 4p to equal 8. Now, remember, focal diameter, you want to think that's a distance, so normally that's always a positive amount. So is our p really going to be 2 here? No, it can't be, because we want our focus on the negative the negative y-axis. So this would have to be at 0, negative 2 in order for the focus to be on the inside of our parabola like this. So our p should actually be minus 2. Now, because of the shape of this parabola and the fact that it's going down, means that this is going to have to look like an equation with the x being squared, and that means it's going to have to be x squared equals 4py, and our p is negative 2, so that forces us to have equation x squared equals negative 8y. Okay? The next type of conic section that we're going to talk about is an ellipse. Geometrically, an ellipse is defined to be the set of all points in the plane, the sum of whose distances from two fixed points, f1 and f2, is a constant. These 2 points are called the foci, which is just the plural of the word focus of the ellipse. So imagine having 2 points inside of our ellipse, f1 and f2, and this time, if you pick any random point, P, on your curve, then the distance between F1 and that point plus the distance between P and F2 is supposed to be a constant amount. So if I move to point P2, then the distance between the focus F1 and P2 and the distance between P2 and F1, if I add up these 2 lengths here, it should be the same length as between here and here. So the sum of these 2 has to equal the sum of these 2. And one way that you could imagine doing this is to take a piece of string that you cut a fixed length of, so you have a certain length of string, and you tack down 2 of its ends at these 2 foci. And then you take a pencil and you drag it around this shape, and that is going to form your ellipse. And it's forcing, because your string is a fixed length, it's forcing this length plus this length to always be the same amount, because it's just the length of the string. So the set of points that does that is called our ellipse. So what we're going to do is derive the formula for an ellipse, and I'll warn you ahead of time, this proof or this derivation that we're going to do is a little bit yucky because there's a lot of algebra involved, but it's all algebra that you know how to do. It's just a little messy because of all the variables that we're going to be talking about. So here's what we're going to start with. Here's our ellipse. We're going to call our two foci F1 and F2, and we're going to center our ellipse so that those two foci are on opposite sides of the origin. So F2 is at positive C and F1 is at negative C. So what we know is that the distance from P to F1 right here plus the distance from P to F2, so this distance here, has to be that fixed length, that length of the string, for example. So in order to make this be some constant, we're going to call that constant length 2a. And we'll see how that a plays into our final formula at the end. So the distance between the point and focus 1 plus the distance between the point and focus 2 has to be this constant amount, and this has to be true for every single point P. So let's write down what the formulas would look like for these two distances. And we're just going to use our distance formula, which is the square root of the difference in the x's squared. So this x minus this x, so x minus negative c quantity squared, plus the difference in the y's squared. So this y minus 0, which would just be y squared. So that's P to F1. Now we're going to do the same thing between P and F2. So the difference in the x's squared, so this x minus c quantity squared, plus the difference in the y squared, y minus 0 is just going to stay y. So here's what we have so far. This double negative becomes plus, and if we take a look at this big mess that we have, in order to make it a little bit easier to deal with, what I'm going to do is separate our two square roots by subtracting this entire square root on the right over to the other side. So this becomes the square root of x plus c quantity squared plus y squared equals 2a minus the square root of the quantity x minus c squared plus y squared. Now what I really want to do is get rid of these squares, or excuse me, the square roots. So what I'm going to do is I'm going to square both sides. So if I square the left side, the square root just disappears, and I get the quantity x plus c squared plus y squared. On the right side, it's not that simple. We don't just get to square the 2a and the square root, because you have to FOIL. So there is going to be a middle term. Now we will get the 2a squared, which becomes the 2a quantity squared becomes 4a squared. And we will get to square away this square root, giving me x minus c quantity squared plus y squared. And that would be a minus times a minus, so that'll be plus. But in the middle, we'll get a 2a times this big square root, and we'll get two of those, one for each of the middle terms. So that middle term is going to look like a minus, because this is a minus, 4a square root of all this stuff. So that's just FOIL. So now what we're going to do is we're going to try to clean this up a little bit. I'm going to go ahead and FOIL out these parentheses here and these parentheses here, and hope that some of these things will cancel out. Now one thing that hopefully you can see will cancel out are these y squareds. We've got a plus y squared on both sides, so if I were to subtract y squared, it's going to cancel out. So let's just get rid of that while we're at it. And now if I FOIL this out, I'm going to get an x squared plus a 2xc plus a c squared. And on the right side, I still have this 4a squared minus 4a times this great big square root. And then if I FOIL out x minus c quantity squared, we get x squared minus 2xc plus c squared. So what I'm going to do next is notice that the x squareds again will cancel because they're both positive, and the c squareds will both cancel because they're both positive. So what I'm going to be left with are these middle terms, which do not cancel because this one's plus and this one's minus. So I'm going to go ahead and add this 2xc over to the left side and take a look at what we have so far. Okay, now I still need to get rid of this big square root right here. So what I'm going to do, oops, this should be a 4xc, excuse me, that was a typo. 2 plus 2 is 4. So we have to get rid of this big square root, but one thing that I notice is since all these terms have a 4, we can go ahead and divide through by that coefficient of 4 just to help clean things up a little bit. And then, in order to try and get rid of this last square root that's remaining, we're going to want to try to isolate it. Now you can do this in several different ways. What I'm going to do is go ahead and add this whole big square root over to the left side, just to make it turn positive. And these are optional steps. You don't have to do this if you don't want to. And while I'm at it, I'm going to subtract this xc over to the right side, because I want to try to get the square root as isolated as I possibly can. So next what I'm going to do is go ahead and square both sides again. And when I square the left side, this a out front gets squared, but it's going to be multiplied by this whole big square root that's being squared. And the square root finally cancel out, but we still need these outer parentheses because that a squared that's out front is eventually going to need to get distributed across. So on the right side, we have this a squared minus xc quantity squared. And what we're going to do next is actually FOIL that out, and we're going to FOIL out here and distribute here, and we're going to try to get rid of all of these parentheses. As I said, it's pretty messy, but really all we're doing is squaring and multiplying, adding and subtracting. So it's all very elementary addition, subtraction, multiplication, division kind of things, but it's just a little confusing because of all the variables. So let's start in these parentheses. We're going to get an x squared minus a 2xc plus a c squared plus a y squared. On this side, if we FOIL this out, we're going to get a squared times a squared is a to the 4th. We're going to get an xc times an xc, which is an x squared c squared, and that'll be positive. And in the middle, we'll get an a squared times an xc, but we'll get 2 of them. So we'll have a minus 2 a squared xc. Now let's distribute our a squared across to all 4 of these. So I have a squared x squared minus 2a squared xc plus a squared c squared plus a squared y squared. Now if we're lucky, maybe something will cancel out. Our negative 2a squared xc is the same on both sides, and they're both negative, which means they will cancel out when I add that term to both sides. So those do cancel out. Unfortunately, that's all that cancels out. So the next thing that I'm going to do is I'm going to try and get my x's and my y's on one side of the equation, and anything that doesn't have an x or a y, I'm going to move to the other side. So I have an x term here and a y term here, so I'm going to leave those where they are. This has an x, so I'm going to subtract it over to the left side. And this does not have an x or a y, so I'm going to subtract it over to the right side. So what we'll have left is a squared x squared minus this x squared c squared. This is gone, and then we have our a squared y squared. These are gone, and on the right side I have that a to the 4th minus that a squared c squared. Alright, we're getting closer. The next thing I want to do is notice that these two terms both have an x squared. So I am going to factor out an x squared from both of them. And these two terms have an a squared in common, so I'm going to factor out an a squared from both of them. And now what I'm going to do is divide through by both of these factors on the right-hand side. So I'm going to divide through by a squared and this a squared minus c squared, and I need to do that to both of these terms on the left side. So we're dividing by both. And what that's going to leave me with on the right side is, since these are both being divided out, you're just going to have a 1 on the right side. For this x squared term, these guys cancel out, so we're left with x squared over a squared. And for the y squared term, the a squareds cancel out, leaving us with a y squared over this a squared minus c squared. Alright, we're just about done. All we're going to do now is we're going to define a new variable, b squared, to be this difference between a squared and c squared. So this equation will now become x squared over a squared plus y squared over b squared equals to 1, where b squared is defined to be a squared minus c squared. And that is the equation of our ellipse. So kind of a tricky derivation here, but really just a lot of multiplication and FOIL and squaring going on, but we were able to work through it all. What you want to notice about this equation to recognize that something is an ellipse is that you have a 1 over here for your constant, you've got an x squared term plus a y squared term, and then you've got these perfect squares down in the denominator as well, and there's a relationship between the a squared, the b squared, and then that c squared, which comes from that foci, from those two foci. So let's generalize what we just came up with. So these are the two different ways that you might see an ellipse. We are going to assume for both of these cases that a is always the bigger number. So we're going to assume that a is the larger number, therefore the a squared is the larger square. So if the a is the larger square and it's underneath the x, then what you're going to see is an ellipse that's shaped like this, where you go a to the right and a to the left because the a is under the x. That tells you how much to go to the left and to the right on the x-axis. And then the b is going to tell you how much to go up and down since it's underneath the y. So look at your variable on top to tell you in which direction to move. So I go a to the right and a to the left, and b up and b down. And because the a is bigger, we're going to have a longer horizontal length going across here than this vertical length. So this going across is called your major axis, and it's just going to have a length of 2a because we go a to the right and a to the left. The smaller direction, in this case the vertical direction, is called our minor axis, and it has a length of 2b. We call our vertices the two endpoints on that major axis. So this a and this minus a. So we could write that as plus or minus a comma 0. And then our foci are always going to be inside of our ellipse at this number c, c to the right and c to the left. And how do you get c? Well, c comes from taking the bigger square, the a squared, minus the b squared, the smaller square. So I always kind of remember this as the bigger square minus the smaller square. Sometimes for me it's confusing to remember which one's A, which one's B, so I always do bigger minus smaller to guarantee that that's a positive difference, and that's how I figure out my C. So what happens if the bigger number isn't under the x? So what happens if A is still the bigger number, but this time it's under y instead of under x? So that means your major axis is now going to be vertical, and we'd go up A and down A, so our vertical major axis would be length 2a, and our minor axis, the smaller one, would be b to the right and b to the left, so it would have a length of 2b. Since the major axis was vertical, these 2 points on the top and the bottom of our ellipse would be our vertices, so their x value would be 0, and their y coordinates would be that plus or minus a, whatever that bigger square root number is. And then it's the same relationship for c squared. It's still the a squared minus the b squared, the bigger square minus the smaller square. But this time your foci are going to be on that y-axis, so they would be in the y coordinate right here. All right, let's try some examples. So first we want to find the vertices, foci, the length of the major and minor axis, and sketch the graph for each of the following. So here's my ellipse. So the first thing we want to do when we're doing our graph is recognize which of these is the bigger square, in this case 25 is, and we've got also this 16. Now the 16 is underneath the x, so that's going to tell us how far to the left and to the right we go on our x-axis using the square root of this number that's in the denominator. So I want to go 4 to the right and 4 to the left. And then the square root of the number that's under the y squared is going to tell me how far up and down to go. So I want to go up 5 and down 5. So immediately we can draw this ellipse. The graphing part is actually really easy to do. Finding all these other things sometimes takes a little bit more work. Now the major axis is going to be the bigger one. And since our bigger square was under the y, that means our major axis is vertical right here. And what would its length be? Well, we go 5 up and 5 down, so it's a total length of 10. Our minor axis, therefore, is the horizontal one, and we go 4 to the right and 4 to the left, so that's a total length of 8. The vertices are defined to be the 2 endpoints on the major axis. So that would be this point here and this point here. So if we wanted to generalize those points, they both have an x-coordinate of 0, and then the y-coordinates would be either plus or minus 5. Now the last thing we need to do is find the foci. And your foci are always going to be along that major axis, so somewhere along here, along that y-axis. And in order to find the coordinates of your foci, you need to find those c's. So remember our definition, c squared is equal to a squared minus b squared, where you're doing the bigger square minus the smaller square. So in this problem, our bigger square is the 25, our smaller square is the 16. 25 minus 16 is going to be 9, so c is going to be either plus or minus 3. So our foci are going to be at 3 going up and 3 going down, or if you want to generalize that, it would be 0 for the x-coordinate and plus or minus 3. Okay, let's try another example. Now this one doesn't necessarily look like our ellipse, so what we want to do first is turn it into our ellipse formula. And you always know that you have an ellipse if you have a 1 on this side, you need an x squared and a y squared, and it has to be a plus in between. So the key thing to do to turn this into that nice ellipse formula is to first get the 1 on the right hand side, which means we're going to need to get rid of this 5, and we can do that by dividing every single term by 5. So this becomes 1, and then we get 4x squared when we simplify that, plus 4y squared over 5. Now this is kind of tricky what we're going to do next, but think about what this is. When we see an ellipse, usually we see the x squared by itself, and then we see a number underneath it. And likewise for the y. We see the y squared by itself on top, and then some square underneath it. That's what we want to try to turn this into. So how do I get rid of this 4 on top? Well, right now it's being multiplied by 4, so think about what would be an alternative to multiplying by 4. Instead of multiplying by 4, we can divide by the reciprocal of 4. And the reciprocal of 4 is 1/4. So x squared divided by 1/4 means exactly the same thing as 4 times x squared, because you would just change this to its reciprocal and multiply instead of divide. Let's try that on this second one. We're going to do the same thing. this wants to be just a y squared. Right now it's 4/5 times y squared. So I'm going to change that multiplication to division, but in order to change the multiplication to division, you have to change to a reciprocal. So instead of multiplying by 4/5, we're going to divide by the reciprocal 5/4. So this is how we changed our equation so that it looks more like our standard elliptical form. Now, which of these two squares on the bottom is bigger? 5/4 is bigger than 1/4. So this is going to be our major axis over here underneath the y. So let's draw our ellipse. Now remember, what you're graphing is not this number, but its square root. So the square root of 5/4 turns into the square root of 5/2. And I don't know what decimal that is, but let's just approximate it to be something up here. And we're going to go up that much, and we're going to go down that much. And since that's my major axis, those are also my vertices. So my vertices are going to be 0 for x and plus or minus the square root of 5/2. Then for the minor axis, that's going to be the square root of this 1/4. And square root of 1/4 is just a half. So we're going to go a half to the right and a half to the left, and those give us 2 more additional points so we can draw our ellipse. So something like that. The major axis is this vertical one right here, and if I do root 5/2 plus another root 5/2, that's 2 root 5/2, which is just root 5. So the total length of this axis is square root of 5. For the minor axis, that's this horizontal distance this way, a half plus a half is just 1. So the last thing we need to figure out is our c, so that we can get our foci. And remember that c squared is your a squared minus your b squared, your bigger square minus your smaller square. So our bigger square is 5/4, our smaller square is 1/4. 5/4 minus 1/4 is 4/4, or just 1. So c squared is 1, which means c is plus or minus 1. So our foci are going to be along the major axis at a height of 1 and down 1 as well. So if we wrote that as points, that would be 0 for the x and plus or minus 1 for the y. Okay, the next example leads us into something a little bit different. It's still an ellipse because we have this 1 on the right side. We still have kind of our x squared, but there's this plus 2 in there. And then we have our y squared as well. So it is the form of an ellipse, but it's now going to take on a slightly different look. And I'm going to generalize this by making it look like this sort of general form for an ellipse. So what we're going to start seeing, it's going to make our problems just a little bit more complicated, is instead of just having x squareds and y squareds, now we might have some shifts involved, shifting our x left or right, shifting our y's up or down at all. And what this does is it creates a new ellipse with a new center. So this is an ellipse that's centered at h, k. And you use the opposite sign of what's in the parentheses because these are horizontal translations, and remember, you go in the opposite direction of what you would expect. So if I see a plus 2 here, we're actually going to go left 2. So our center for our ellipse is no longer going to be centered at the origin. It's going to be shifted left 2, and the y doesn't have any shifts, so that's going to stay centered at 0. So in other words, instead of being centered here, we're just moving it over and now centering it here. Okay, now how does that affect the rest of what's going on? Well, we need to look at our a's and our b's again. So what's the number that's under this y squared? There isn't one, but it's implied to be a 1. So the bigger square here is the 4. So that's going to be our major axis, and the 1 is the smaller square, so that's going to be our minor axis. Now here's where we want to be careful. Since our major axis is under the x, we want to be moving the square root of this number to the left and to the right. But we're not doing it from 0 this time, we're doing it from our center point. So the square root of 4 is 2, and I want to move that in the x direction. So what that means is from this center, I want to go 2 to the right, which would now put me at the origin, and 2 to the left, which would put me over here at -4. And those were my major axes points. So those are also called our vertices. So this vertex on the left actually is at -4, 0, and the vertex on the right is now at 0, 0. And the major axis length is going to be 2 to the right and 2 to the left is a total of 4. Now let's do our minor axis. It had a 1 in the bottom, so the square root of 1 stays 1. So we're going to go from the center up 1 and from the center down 1. And here is now what the graph of our ellipse would look like. And the minor axis now goes up 1 and down 1, so the minor length is going to be 2. So all that's left for us to find is the foci. And because the major axis is horizontal, the foci are going to be on that negative part of the x-axis somewhere. So how do we find them? Well, c squared is a squared minus b squared, and our bigger square was the 4, our smaller square was the 1, 4 minus 1 is 3, and that's what c squared is, so c itself is going to be plus or minus √3. Now here is where we have to be careful again because of this shifted center point. What that means is that your foci are going to be from the center to the right. We're going to add a √3. So from the center, √3 to the right is now where our focus 1 is. And if we go √3 to the left, or subtract √3, that's going to be where our f2 is. So what are our two foci? Let's do the one on the right first. How do we figure out the coordinates of this point on the right? Well, it's the center point for x, which was -2, but then we're adding square root of 3 to it to move it to the right. The y coordinate has not changed, so that's going to stay 0. So this is our f1. Now we're going to do the same thing to get f2, but this time we're going to start at the center, which was -2, and we're going to want to go left, so we're going to subtract √3. And again, we're not changing the y coordinate, so that still stays 0. Okay, on the next two examples, what we're going to notice is that they have some x's and some y's involved. So that doesn't normally show up when we look at our ellipse formula that we've seen in the past. So what we're going to need to do to these is take this example D and this example E and transform it into this generalized form that we have defined up here, which is the equation of ellipse that's been shifted and has a new center at h, k. How do you take something like this and turn it into this sort of factored form? Well, that is called completing the square. So in order to transform this into this, we have to complete the square. And the bad news is we have to complete the square twice. Once for the x's and once for the y's. So let's see how this is going to work. First thing we're going to do is we're going to group our two x terms together. So my x squared and my 20x. Then I like to leave a little bit of space here, and then I'm going to put my two y terms together. So 4y squared minus 40y, and then the constant term, I'm going to just get it out of the way and move it over to the right side by subtracting. So how would we complete the square on these x's? Well, this one's slightly easier because this leading coefficient of x squared is already a 1. So all I need to do is put it into a factored form, and in order for this to match what I originally had, we would have to have an x plus exactly half of this middle term, a 10. in order for this to FOIL back out. And if you were to FOIL it out, you'd get back that x squared, you'd get a 10x, you'd get another 10x, which is that 20x, but what else would you get on the end? You'd get 10 times 10, or 100. So these three things become this factored form. But I didn't have a 100 to begin with in my problem, so I can't just add it in without balancing it out. So what I do is I add that extra 100 also to the right side. And as long as you're doing it to both sides, you're keeping the equation equivalent. Now we're going to do the same process on the y's, but it's actually a little bit trickier because the y squared term has a 4 in front. So what we're going to have to do is pull out our 4 first and factor it out. And I have to factor it out of both of these y terms. So this is going to leave me with a 10y. Now notice what I'm doing. I'm putting some empty space and then I'm closing off my parentheses off to the side. Because when I go to complete the square and make this y minus 1/2 of 10, which is 5, what I'm missing is that 5 squared, or 25, so I need that in there so that these three terms become this. And normally what we would want to do is add that 25 on this side as well to keep it balanced, but I can't do that because we had to factor out that 4 from all these y terms. So where does that 25 get balanced out? What we're going to do is we're going to subtract it right next to the one that we added. So here we really just added a fancy 0. But what I'm going to do next is distribute this 4 across to that minus 25 and also distribute this 4 to my factored form. So now it looks something like this. So what we have next is this situation right here. We're almost there. I'm going to go ahead, and now that I've distributed that 4 across, I can add this 100 over to the other side, and this is now going to become x plus 10 quantity squared plus 4 times y minus 5 quantity squared. And notice what happens on the right side. Negative 300 plus a 200 is a negative 100. And that should kind of give you pause right there. Because think about this left side. You have a quantity squared plus a positive 4 times another quantity squared. How can two squares that are being added together add up to something negative? It can't happen. So this does not have a solution. This is not an ellipse, and it's not going to turn into our nice factored form. So we would stop there, and now we're going to adjust our numbers slightly so that we can fix that problem for part E. So everything is almost identical. I'm going to save my work here and recopy it. Everything is exactly the same as what we just did. So I'm just going to recopy this line right here. Except this time, instead of having a negative 300 on the other side, when I move this over, it was a negative 100 for this particular problem E. And we added a 100 that was balancing out the 100 we got over here. And when I add this 100 over, now we don't end up with a negative anymore. We end up with these canceling out and giving a positive 100 on the right-hand side. So now that's legitimate because we have two squares being added to a positive number. So that can obviously happen. Now to finish it off, to put it into our nice perfect form, ellipses want to have a 1 on this right side. So what I'm going to do is divide every single term by 100, and this becomes x plus 10 quantity squared over 100 plus, let's reduce here a little bit, 4 goes into 100 25 times, and 100 divided by 100 is just a 1. So now we have our nice elliptical form. So let's graph it. Okay, so here's how we graph it. What is the center of this ellipse? Because we have this plus 10, we're actually going to be shifting left 10. So our center is going to now have an x-coordinate of negative 10. And a minus 5 next to that y means we're actually going to shift up 5. So our new center is going to be at -10, +5. So put your dot right there. And now we want to figure out what our a squareds and our b squareds are. The bigger square is the 100. So this is going to be our major axis under the x, so horizontally. So that means the square root of 100 is 10. That means we want to go 10 to the right from our center. So if here's my center, 10 to the right would put me right back on that y-axis, and 10 to the left would put me over here at -20. And those are my two vertices. So the vertex on the left is at -20 for x, and notice it's still at a height of 5 for y. This vertex on the right is at 0 for x and at a height of 5. And what's the major axis length? Since we went 10 to the right and 10 to the left, that's a total length of 20 going across. Alright, now let's do the y direction. Underneath the y we had 25, so that's going to be our minor axis, and the square root of 25 is 5. So from your center, you want to go up 5, so that's going to put me at a height of 10, and I'm going to go down 5, which is going to put me right at 0 on that x-axis. And now we can draw our ellipse like this, and our minor axis length, since we went up 5 and down 5, would be a total of 10. Finally, let's find our foci. And you know that your foci have to be on your major axis, so they are somewhere here and here. Let's call this guy F1 and this guy F2. So to find them, we need to know what our C is. And remember, C squared is a squared minus b squared. The bigger square is the 100. The smaller square is the 25, so that gives me 75. And when you take the square root of 75, you can break that down into a 25 and a 3, so C reduces to 5 root 3, plus or minus. So how do we get our two coordinates of our foci? Well, to get the one to the right, we want to add this C. We want to add 5 root 3 to our center point. So to get F2, we're going to take our center point, which is at -10 for x, and we're adding 5 root 3 to that. Am I doing anything to the height? Am I changing this up or down at all? No. So the y-coordinate is still going to stay 5. To get the other foci point, this time we're going to subtract 5 root 3 because we want to move it to the left. So we take our center point, which for x is -10, and this time we subtract 5 root 3, and we're not changing our height, so that stays 5. So that's a pretty tricky problem. That one has a lot of stuff going on in it. Alright, let's try a few more examples here. Whoops. So on this next one, we want to write the equation of ellipse satisfying the following conditions. Sorry about that, this is being finicky. There we go. So we want our ellipse to have foci at plus or minus 4, 0, and vertices at plus or minus 5, 0. So let's draw a picture of this so we can visualize. Our vertices are at plus or minus 5, 0, so that's on the x-axis. And remember, your vertices are a major axis. So we know that if we're writing our ellipse, it's got to look like an x squared over something plus a y squared over something equals to 1, assuming that we don't have our center shifted at all, which this one does not. So if we're going 5 to the right and 5 to the left, then that distance right there is your A. That's going to be exactly the square of that distance needs to be what goes under your x squared. So this would have to be 25 right here, so that we would know to go 5 to the right and 5 to the left. Now the question is, well, how much up and down do we go? And they don't tell us that, but they do tell us where the foci are. The foci are at 4 and -4 on the x-axis. So how far up and down should my ellipse go That's what we want to figure out, because that's the b squared. That's going to tell me what goes under my y. And the only way to figure that out is to use our relationship that c squared is equal to a squared minus b squared. The bigger square here we know is the 25. We don't know what b squared is. That's what we're trying to figure out to go under our y. But we do know c, because that's what foci are. The foci are always your c's. So c squared is 16. If I subtract 25, this gives me a negative 9. So b squared is equal to positive 9, which means I need to put a 9 under here, and it also implies that b is plus or minus 3. So that's telling me that I need to go up 3 and down 3. So here's the equation of my ellipse. Okay, let's try another one. This time we want our foci to be at 0 plus or minus 5 and have the length of the major axis be 12. So if the foci are at 0, comma, plus or minus 5, that's right here and right here. Now remember, your foci are your c, and they are always on your major axis. So if my major axis is supposed to have a length of 12, how can that happen? Where do my vertices have to be? If this much is 5 and this much is 5, and I want this whole length to be 12, then this has to be at 6 and minus 6 for my two vertices, so that when I draw my ellipse, that major axis has a length of 12. So when I think about my equation of my ellipse again, x squared over something plus y squared over something equals to 1, this 6 is your vertex, and it's your bigger square because it's your major axis. So 6 squared is 36. Where should I put that 36? Should it go under the x or should it go under the y? It needs to go under the y because our major axis here is vertical this time, going up and down. So how far over to the right and to the left should I go? That's what I need to figure out so that I can put that under my x squared. And the only way to figure that out is to use our c. So c squared is equal to a squared minus b squared. The bigger square is the 36 because that was our major axis. We don't know the b squared, and we know c is this 5, so c squared must be 25. When I subtract 36 over to the other side, that gives me negative 11 equals negative b squared. So b squared equals positive 11, and it's that square that goes under our x squared. Just for a side benefit or side knowledge here, that implies that the b itself is square root of 11. So that means I'm going over square root of 11 to the right and square root of 11 to the left. Okay, last example for ellipses. This time we want the endpoints of our minor axis to be 0, comma, plus or minus 3, and we want the distance between our foci to be 6. So let's draw a picture. Our minor axis endpoints are supposed to be plus or minus 3. That's on the y-axis. And that's supposed to be our minor axis. So our major axis would have to be under or along that x-axis. So these distances here need to be longer than this vertical distance here. Where do your foci go? Your foci always go on your major axis. So if the minor axis is vertical, then the major axis is horizontal, and the foci need to go along that horizontal axis. And if the distance between them is 6, the only way that can happen is if I go 3 to the right and 3 to the left, so that this whole distance is 6. So what is the c itself? Remember, c is the coordinate of your foci. So since I'm going 3 to the right, my foci are plus or minus 3, comma 0. So c is 3. What does this minor axis tell us? That's your smaller square. Remember, that's your b. So in this case, we're going up 3 and down 3, so we know that our b is 3. So let's see what we have. We're trying to come up with the equation of our ellipse. So it needs to look like an x squared over something plus a y squared over something equals to 1. We don't know what the bigger square is yet because we don't know what the major axis is yet, but we do know that the major axis needs to be under the x because it's horizontal, and the minor axis is under the y, and we do know that because we went 3 up and 3 down, and 3 squared would be 9. So this has to be a 9. So all we need to do now is find this bigger square, this a squared. So let's use our c to help us out. C squared is a squared minus b squared. We know that our c was 3, so that becomes a 9. We don't know the a squared, the bigger square, but we do know our b is 3, so 3 squared would be 9. If I add that 9 over to the other side, we get 18 is equal to a squared, so this is going to be 18. And by the way, that tells us again that a would be square root of 18, which is the same as 3 root 2. So we're going 3 root 2 to the right and 3 root 2 to the left. But here's our equation that we're trying to come up with. Okay, our last type of conic section that we're going to talk about is a hyperbola. And it's very similar in its definition to an ellipse with one slight change. A hyperbola is the set of all points in the plane, the difference of whose distances from two fixed points f1 and f2 is a constant. The two fixed points again are called the foci of the hyperbola. So what's different here is we're going to have two foci again, and we're looking at the distance between that foci and your point P and the other foci and your point P. But instead of, in the case of an ellipse, where these add up to a constant, for a hyperbola they subtract to a constant. So that's the only difference in the actual derivation of the proof. But you end up with a vastly different looking picture. The hyperbola looks like these two branches with the foci being on the inside. They almost kind of look like parabolas almost, but we'll see a slight change when we get into more detail on the graph. Now I'm not going to do the full proof of the derivation of the formula for the hyperbola, and you're probably glad about that, but I am going to just mention a couple of key ideas. So what we're basically saying in regards to this picture is that we want the distance from point P to foci 1 minus the distance from point P to foci 2 to be this constant, and we're going to call it this plus or minus 2a. And then what you would do to figure this out is you would actually compute those differences. So this distance would be the difference in the x's, so x minus negative c, so this x minus this x, quantity squared, plus this y minus 0, which would just leave it as y. And then over here you would do the square root of the difference in these two x's, so x minus c, quantity squared, plus this y minus 0, which is just going to stay y. So it's very, very similar to the ellipse. And then we're not going to do all the work because it takes a long time to do, and it's almost identical to what we did for the ellipse, but you would add the square root over, square both sides, complete this, or finish foiling out and canceling terms out and so forth. And what you end up with for your final equation in its most simplified form is x squared over a squared minus y squared over b squared is equal to 1, where we're defining b squared to be that foci constant c squared minus a squared. So this is the formula for a hyperbola. Now look at how similar it is to the ellipse. It's almost identical. The only difference is you have subtraction instead of addition. The other slight difference is in our formula. Instead of letting c squared be b squared minus a squared, if you notice, you could add this a squared to the other side, and that would tell you that c squared is a squared plus b squared in the case of a hyperbola. So that's the other slight change. So let's put this together into some important ideas. So here is what our two possible equations might look like. In the first case, if the x comes first, then you are going to have your two vertices be at plus a and minus a, whatever that square root of that number is underneath the x. So what you'll see are these two dots at a and minus a on your x-axis. Then what we do is we take the square root of the number under b, which would the square root of the number under y, which would be just b, and those aren't going to actually be points on our graph, but we still go up b and down b. And then what we do is we construct this imaginary box. And then what we're going to do is draw in the two diagonals of that imaginary box. And those are called your transverse axes. And they are going to, those are called your asymptotes. Sorry about that. Those are called your asymptotes, and they have as their equation y equals plus or minus ba over x. Now, why would they have an equation like that? Well, they're lines, so it should be a linear equation. They go through the origin, so there's no b on the side, there's no plus b, and the slope of this line would be going up b and over a, so that's where this b over a comes from. Now the transverse axes is kind of like our major axes when we talk about an ellipse. It's just this length going across here, which has a length of 2a, because we go a to the right and a to the left. So that's kind of like your major axes. And then your foci, again, are going to be 2 points. They should be inside of your two branches of your hyperbola, and they would be at c comma 0 and negative c comma 0, with the relationship that c squared is always this a squared plus this b squared. Now, if you have your equation with the y term coming first, then instead of having your branches go right and left, now your branches are going to go up and down. So the square root of the number underneath our y term, so in this case a, we're going to go up and down that amount, and those are going to be called our vertices, and that also forms our transverse axis. And then the number under the x, we're going to take the square root of that, and we're not going to plot any points, but we're going to mark some little marks here so that we can create the box that is formed by going b to the right, b to the left, up a, and down a. So we get this imaginary little box. Then we draw our two asymptotes, and then what we get for our actual final graph of our hyperbola is this arcing branch going up that's squeezed in between these two asymptotes, and this arcing branch going down that's squeezed in between these two asymptotes that's centered at these two vertices, a and minus a. So here's what I kind of do when I'm trying to sketch these things. First, I mark the a's and the b's on my two axes, and I draw that central box. Then I sketch in my asymptotes, I put dots at my two vertices, and then I show those two branches. So let's practice. Find the vertices, foci, and asymptotes of the hyperbola and sketch its graph. So here's my equation. What's important to note when you're doing your hyperbolas is which variable comes first, because it's that variable where your vertices are going to be. So since y is coming first, that's going to be what we call our transverse axes. And the square root of 9 is 3, so that means I want to go up 3, put a dot, and down 3, put a dot. And those are called your vertices. So our vertices have 0 for x and either plus or minus 3 for y. And those are going to be actual dots on our hyperbolas. Now what we want to do is go out the square root of 16 on the x-axis. So square root of 16 is 4. So I'm going to go 4 to the right and 4 to the left. And I'm not actually making any marks, but what I'm going to do is I'm going to draw in this little box. You can make it dashed lines or solid lines. It doesn't really matter. What's important is we're going to draw the diagonals, because those diagonals become our asymptotes. And then to get the final sketch of our graph, we go back to those dots where we had our vertices, and that's kind of the center of each of our branches. And then our branches are going to be squeezed in between these two asymptotes. So one branch points up and one branch points down, squeezed in between our asymptotes like that. Alright, so we got our graph, we've got our vertices. Let's find our foci next, our two different focus points. So they are going to be somewhere inside of these two branches, like this and like this. So to figure them out, you need to know those C's, because your foci always occur at the C's. So our formula for C with hyperbolas is a little different than the one for the ellipse. This time C squared is always your A squared plus your B squared. So that's always going to be these two squares added up. And it doesn't really matter which one's the bigger one or the smaller one when you're talking about your hyperbolas. So this is just going to be 9 plus 16, which is 25. So C is going to be plus or minus 5. And since these are on our y-axis, that means our foci have an x value of 0 and a y value of plus or minus 5. Now the last thing we have to figure out are the equations of these two asymptotes, and to figure them out we just need to find out what their slopes are. So start at the origin and let's just count rise over run. Here we rise up 3 and we go over 4, so this line has a slope of 3/4, so its equation is going to be y equals 3/4 x, and there's no plus b on the side because it goes through the origin. The other asymptote is exactly the same, but this time we go up 3 and left 4, so its slope is going to be negative 3/4. So those are my two asymptotes. Okay? Alright, let's try another one. Now this one doesn't look anything like that last example when you look at the initial equation. So what we need to do is transform it by putting it into that equation, and the key to doing that is getting that 1 on the right hand side. Both the ellipse and the hyperbola are always supposed to be equal to 1. So the first thing I'm going to do is divide every single thing by 3. So this gives me x squared over 3 minus minus 2y squared over 3 equals to 1. Now we did an example like this earlier when we were doing our ellipses. We really would like this to be an a squared by itself over an x squared minus a y squared by itself over a b squared equals to 1. So we want to get rid of any coefficients. Well, this one's okay. This one's good to go because the x squared is by itself on top. So I don't need to do anything to that. But this one has a 2 next to the y squared. So think of this as 2/3 times y squared. So what we're going to do is instead of multiplying by 2/3, we're going to divide by 3/2 because those mean the same thing. Multiplying by 2/3 is the same as dividing by 3/2, the reciprocal. So all I did is I changed this by flipping it over, and now I have that y squared by itself, and now this is in the proper form that I want it to be in. Okay, which variable comes first? That's what's important when you're dealing with a hyperbola. The x comes first, so that means I want my vertices to be on the x-axis, and the vertices are going to be at the square root of this number. So that would be the square root of 3. So that's somewhere over here to the right and somewhere over here to the left, and those would be your vertices. And they're on the x-axis, so plus or minus square root of 3, comma 0. I'm going to put dots on those. Then I'm going to look at this number and take its square root, and square root of 3/2, which would be like this, is actually smaller than the square root of 3. So it's not going to be quite as tall, but it would be somewhere up here and somewhere down here. And those aren't actually points, but I need to know how high and how low they are so we can construct our box. So it's going to look something like that, and then I'm going to draw in my two diagonals, which are going to be my asymptotes. And then to draw the actual hyperbola, go back to your vertices, and that's your sort of almost vertex, if you will, and sketch your branch so that it's squeezed in between those two asymptotes. And my graphing here is kind of crooked looking, but you want to use your imagination there. Okay, so something kind of like that. So there's our graph. We have our vertices. Let's find our foci, which should be somewhere inside of each of those branches. So to get the foci, we need to know what c is. So c squared, remember, is a squared plus b squared, or this number plus this number. So 3 plus 3 halves. And if I get a common denominator there of 2, 3 is 6 halves, plus 3 halves makes this 9 halves. And if I take the square root of that, that's going to be the square root of 9, which is 3, over the square root of 2. And if you wanted to rationalize, that's 3 root 2 over 2. So this would be 3 root 2 over 2, and this would be negative 3 root 2 over 2. So the coordinates of my foci, they're on the x-axis, so plus or minus 3 root 2 over 2, and the y-coordinate there is 0. Last thing we want to do is find the equation of our two asymptotes. So let's think about slope. You want to go up root 3 halves over this vertex, which is at root 3. It kind of got erased there a little bit. So I go up, my run here is the square root of 3 over 2. Sorry, not my run. My rise is that square root of 3 halves, and my run, how far over I go, was this square root of 3. So let's see if we can clean that up a little bit. This is like a root 3 over a root 2 divided by a root 3. So if we think of that root 3 in the bottom as being root 3 over 1, we can change this division to multiplication by the reciprocal of the denominator. So I'm going to leave the top alone, and I'm going to flip over the bottom fraction so that these will cancel out, giving me 1 over root 2, or if you rationalize, root 2 over 2. So that means the slope of this line right here is root 2 over 2, so its equation is y equals root 2 over 2x. And the other one is exactly the same, but just minus. So y equals minus root 2 over 2 times x. So a little bit messy there, but doable. Okay, now we're going to get into our shifts again. So this time what I want you to think about is those formulas for our ellipse and for our hyperbola can be generalized to include shifts in the center. So you can have either x minus h quantity squared over a squared minus y minus k quantity squared over b squared equals 1, or you could have the y coming first. It doesn't really matter. I'm not even going to write it because we're not going to have enough room for everything else. So it could be this form, or it could be like this one is and have the y's come first. It doesn't really matter. But this is an hyperbola because it has the minus. All right, that's the giveaway. And because we have these parentheses with the numbers inside, remember that is going to cause us to have a shifted center. So instead of being centered at the origin, 0, 0, we need to move things around. Now look at the variable that is in the parentheses with the number to tell you which coordinate you're talking about. If I see y here and I think, okay, this is a minus 1, so I actually want a plus 1, you need that plus 1 to be y because it's next to y. And over here I see a plus 3, so I should think minus 3, and since it's next to that x, that needs to be the x coordinate. So my new shifted center is going to be negative 3, comma 1. Put a dot right there. Now that's not actually going to be on our hyperbola, but we have to know that dot in order to be able to figure out everything else that we're going to be drawing in. So what do we do next? We look at which variable came first. It was the y. So that means our transverse axis is going to be in the y direction, up and down. So our vertices are going to be up and down as well. And where are they going to be? Well, they're going to be up and down 5, since the square root of 25 is 5. But since we have a shifted center, we need to go up 5 from the center and down 5 from the center. So let's see what that would put us at. I would go up 5, 1, 2, 3, 4, 5 would put me right here. And that has as its coordinates -3 still for the x, but now the height is at 6. And then we're going to go down 5 for the other vertex. So down 5 would put me at still -3 for the x, because I didn't move left or right at all, but my new y value is -4. So those are my vertices. Then we would normally look at what's underneath our x squared, and there doesn't appear to be anything there, but you need to know that that implies that it's a 1. So the square root of 1 stays 1. So then what we would normally do is go from our center, right 1, and just put a little dot there, and left 1. And those really aren't dots on our graph, but we need to know them in order to draw our box. So let me use a different color here for my box. Here's what my box would look like. And then my asymptotes would be along these diagonals, right through that center. And then to get the final graph itself, you're going to go back to your two vertices and you're going to draw your two branches, one going down in this case and one going up. So there's the graph. We've got our vertices. Let's find our foci next, which should be somewhere up here and somewhere down here inside of your two branches. So to get your foci, you need to know what c is. So c squared is a squared plus b squared. So this squared plus this squared. So that's 25 plus 1, which is 26. So c is plus or minus square root of 26. Now, because we have a shifted center, this is going to complicate things. So our foci are not just going to be 0, comma, plus or minus root 26 anymore. We have to go up square root of 26 and down square root of 26 from our center point. So to find the coordinates of these 2 points right here and here, let's call this one F1 and this one F2. To find F1, what we need to notice is all of these points in red here, what are their x coordinates? They're -3. That's not changing because I didn't move left or right at all. But what will change are the y coordinates. The y coordinate of our center was 1, and what we're going to do to get our foci is we're going to add square root of 26 to that value. So the new y coordinate would be 1 plus square root of 26. Then to get F2, we're still not changing x, it's still at -3, but this time we're going to take this center point 1 and we're going to subtract square root of 26 from it to find out how low this second foci point should be. Alright, last but not least, the asymptotes, and this is a little bit tricky, okay? So here's what we're going to do. First, let's find the slope of our asymptotes. And to figure out our slope, go from your center and figure out how far up and over we go. What's our rise over our run from the center to the corner point. I rise up whatever that vertex amount was. And in this problem, that was this 5. So I went up 5 and I went over whatever the square root of this number was, which was 1. So my slope is 5 or minus 5 in the other direction. So plus or minus 5. So that should be the slope of my asymptote. Remember, that's the b over the a. The problem is my asymptotes are not going to be this time just plus or minus that slope 5 times x. That would only be true if the line went through the origin. And notice, because we have a shifted center, these two asymptotes do not go through the origin anymore. So what we're going to have to do is use the center point together with the slope that we know we're supposed to have, and use point, slope, form to come up with the equation of these two new asymptotes. So we're going to use point, slope, form, using the center, which is at -3, 1, because we know that that is a point that lies on our asymptote because it went right through the center of my box. And then I'm going to use my slope, and for the asymptote that's pointing up and rising up, that was +5. So the way point slope form works is y minus y1 equals the slope m times x minus x1. So we want to do y minus 1, this y coordinate, equals our slope, which we want to be 5, parentheses x minus this x coordinate. So we get a double negative there, which becomes plus. Y minus 1 gives us 5x plus 15, and if I add 1 to the other side, one of my asymptotes is y equals 5x plus 16. Now, what about the other one? What changes when I try to find the asymptote that falls, this other one on the other diagonal? The only thing that's different is the slope. It's still going through -3, 1, but this time the slope is -5 because it's falling. So we're going to do this all over again, but this time we're going to use a -5 for our slope m. So y minus 1 equals -5, parentheses, x minus a -3, which becomes +3. And that gives me y minus 1 equals -5x minus 15. And when I add 1, we get y equals -5x minus 14. So those are my two asymptotes. All right, let's try another one. Now on this next example, what you see are some extra x's and y's in there. And as soon as you see something like that in this kind of a problem, we encountered this when we were doing our ellipses as well, is you want to be thinking complete the square. That's what it's going to take to do this problem. So we need to complete the square twice, once for the x's and once for the y's. So here's what we're going to do. First thing we're going to do is get our two x terms together. So I'm going to get this x squared and this 10x together, so I'm going to have to subtract my 10x over to the left side. Then I'm going to leave some space, because that's where my extra number that I need to add in is going to go. Then I'm going to get my two y terms together. So this y, and it does have a minus in front of it, and I'm going to have to add the 10y over to the left side. Leave some space, and then this 1 is my constant, and it's just going to stay on the right side. And now we're ready to complete the square on the x's and the y's. So for the x's, it's ready to go. All I have to do is take half of that middle term. So this is going to be x minus 5 quantity squared. If I were to FOIL that out, I'd get an x squared. In the middle, I'd get a minus 10x. But on the end, I'd get a positive 25. So I have to balance that out by adding 25 to the other side as well. So now these three things factor into that. Now for the y's, not quite as easy, because I have that minus in front of the y squared. So first we have to factor out the minus. So this changes it to y squared minus 10y. Leave some space inside of your parentheses, because whatever we add in, we're going to have to subtract it in here as well, inside of these parentheses. And then we're going to have to distribute that negative across before we can try to combine it with these numbers over here. So how does this inside stuff factor? Well, it would have to have a y minus a 5 as well, quantity squared. If you were to FOIL that out, you'd get the y squared, you'd get the minus 10y, but you'd also get a plus 25. Now to balance it out, instead of adding that to the other side, I need to subtract it off inside of my parentheses, because these three become this with that minus out front, and then I need to distribute my negative across first before I can start combining it with these other numbers on the right side. And so what I'm actually going to end up needing to do is subtract it over to the right side. And these cancel out, giving me just 1. And what I'm left with over here is the x minus 5 squared minus the y minus 5 quantity squared. Now, does that look like a hyperbola? It should, because it is. It has the x squared, it has the y squared, it has the 1, and there is subtraction. What makes it look a little bit funny is that it's not being divided by anything, but it really is. It's just being divided by 1. So it is a hyperbola, it just looks a little bit different because it's actually a little bit simpler. So here's what we're going to do. We're going to graph it, and we're going to notice that because it's the x term that comes first, we want to be graphing our branches along the x direction, but because we have these parentheses, we have a shifted center. Plus 5 for x, plus 5 for y. So let's draw that center point first, and then what we're supposed to do is we're going to take the square root of this 1, which would just be 1, and we're supposed to go from our center right 1 and left 1 from that center. And those are your two vertices. And we went right and left because this was x, and x is going right and left. So what are the coordinates of these two vertices? Well, the one on the right would now be at 6, 5, and the one on the left would now be at 4, 5. One more than 5 and one less than 5. Now we're going to take the square root of this number, which is also 1, and that's how far up and down we're going to go from our center point. So we're going to go up 1 and down 1, and it's from that we get our little box. And then we're going to have our two diagonals going through the center point. And then to get our graph, we go back to our two vertices, which were these side ones along the x direction, and we squeeze our graph in and show those two branches. So that would be what our hyperbola looks like. Let's find the foci next, and they would have to be somewhere over here and over here. So let's find what our c squared is going to be. It's supposed to be a squared plus b squared, which is this plus this. So 1 plus 1 is 2. So that means c is plus or minus root 2. So what are our foci going to be? Well, our foci, remember, are based on that center point. So here's that center point right here, and we want to go to the right square root of 2. So how would I figure out what the coordinates of this point on the right is? Well, it's what the center was originally, which was 5, 5, and I'm adding to the x value that root 2. I'm not changing the height at all, so the height is still 5. To go the other way, to get the other foci, we're going to still start at 5 for x, but this time we're going to subtract that root 2, that c value, and we're still staying at a height of 5. So your foci should always be your center plus or minus your c. Okay? Alright, the last thing we need are those asymptotes again. So let's think about what the slope of our box is, and it's kind of tiny here, so it's kind of hard to see, but thinking about your center point, which is right in the middle, I go up 1 and over 1 to get to that corner. So the slope of our box is 1 if we're going up, and it would be minus 1 if we were going down. So what do we do to find our asymptotes? You have to use your center point in conjunction with these two slopes, either plus or minus 1. And we're going to do just like we did in the last problem and use point slope form, because our asymptotes go through this center point. So we're going to do y minus this y coordinate 5 equals our positive slope of 1, parentheses x minus the x coordinate. So that's going to give me y minus 5 equals x minus 5, and if I add 5 to the other side, they cancel out, so one of my asymptotes is just y equals x. Now let's do the other one. So still y minus 5, but this time we're going to use negative 1 for our slope times x minus 5. When I distribute my negative, we get negative x plus 5, So when I add 5 to the other side, this time it doesn't cancel out, and I get negative x plus 10. So those are my two asymptotes. Okay, to finish up, we're just going to come up with the equation of our hyperbola satisfying the following conditions. So we want our foci to be at 0, plus or minus 10, and our vertices to be at 0, plus or minus 8. So let's visualize what this would have to look like. I'm going to start with my vertices because those are on my actual hyperbola. We want to be at 0, plus or minus 8. So that means they're on the y-axis, up 8 and down 8. And so what this would look like would have to be something kind of like this. And our foci are going to lie inside of those, and we happen to know what the foci are. This is 10, and this is minus 10. So that's your C right there. And remember, for your vertices, those are going to be your A. And which variable should it go underneath? Remember, the equation of a hyperbola looks something like this. It's either x squared over a squared minus y squared over b squared equals 1, or it's y squared over a squared minus x squared over b squared equals to 1. Which one of these do we want? Since our hyperbolas have vertices on the y-axis, we want that square of 8 to be underneath the y variable, since we're on the y-axis. So we need this version of the formula. 8 squared is 64, so we need this to be y squared over 64. So now we know what that first part is. We just need to figure out what the b is so that we can plug it in. If we can figure out what b squared is, then we'll have our equation. Well, if you know c and you know a, you can find b, because the relationship for a hyperbola is that c squared equals a squared plus b squared. C is your foci always. So 10 squared is 100. The a squared was the 64. So if I solve this for b squared, 100 minus 64 is 36. So that's our b squared. And I'm going to just put that 36 right down here. What that also tells me is that my b is plus or minus 6, which means we would go out 6 to the right and 6 to the left. And that's kind of how we would get our box. And then we could draw this graph a little bit more detailed, because we would know exactly where those asymptotes should go. Alright, last example. This time we want to find the equation of our hyperbola that has vertices at 0, plus or minus 6. So right away, just like the last problem, that's along the y-axis. So I want to go up 6 and down 6. And those are dots. And that means, since they're on the y-axis, my two branches have to be pointing up and pointing down. And that means I have to have the y squared term coming first minus the x squared term. And I even know what needs to go under that y squared, because that's exactly what your vertices give you. If the vertex is at 6, then 6 squared is 36, and that is what has to be under that y squared. So how am I going to find out this b squared over here if I know a squared? In the last problem, we happened to know the foci, so we knew c and we knew a, so we could find b. In this one, it's not as obvious, because you know what the a is. That's what this 6 is, but we aren't told the foci at all. All we're told are these asymptotes. So there must be enough information in order to figure this out. So let's think about what it tells us. Remember, your asymptotes come from this box. And the slope of this diagonal line is supposed to be 1/3. And your slope here is coming from this rise, which we already know is 6, over this run, which we don't know. That's going to be our A here. So 6 divided by A is supposed to equal 1/3. So we're going to use this equation to help us solve for our A, our missing A. So how do you solve this? It's just a proportion. I can cross multiply. 3 times 6 is 18, a times 1 is a, and if you square that, a squared is 324, so that is what goes under our x squared. So I didn't even need to know c at all here, because I could get it from the slope of my asymptote. So here's the equation of our hyperbola, and we're all done. That concludes our lecture on conic sections. It's a lot of information. This was a long lecture. Please make sure that you look over those 3 formulas for your parabolas, your ellipses, and your hyperbolas really carefully and know them really well. Good luck.